Okay, let me start recording. I think today is actually relatively short, and I don't think is terribly difficult. It kind of depends though. Depending on how you feel about isomorphisms. How many students enrolled in this course? I think it's still like 164. So almost nobody has dropped. Yeah, but that's okay. Maybe we're just doing a great job. Yeah, okay. So if you have a solid understanding of isomorphisms, and remember, isomorphisms mean that the two groups are the same, right? If G and H are isomorphic, then they're really the same group. Now, there's a sense in which the things that we're going to study today, called automorphisms, they're interesting and they're important, but not for the same reason as isomorphisms are important. Let me just write it down, and I'll show you what I mean by that. Okay, so today we're going to talk about automorphisms. It's a weird word. There are lots of different kind of morphisms in the world, right? We've learned about homomorphisms. We learned about isomorphisms. There's also automorphisms, endomorphisms, monomorphisms, epimorphisms, yada, things that we just call morphisms. They're all different types of functions. So what is an automorphism? If you think about what the word auto means self, right? That's what auto means. So an automorphism of a group G is an isomorphism from G to itself. Oh, where'd the P go? Okay, so that's what automorphism means in this case. And again, auto means self, so it maps G to itself. Now, we already knew that G was isomorphic to G. That's silly, right? We don't need to somehow convince ourselves that G is the same group as G. They're trivially the same. But nonetheless, automorphisms end up being this really kind of interesting way of studying a group. It turns out you can learn a lot about a group by studying its automorphisms. Okay, so this is kind of an interesting thing. Now, we've seen an example of this in the worksheet on Thursday, right? So from Thursday's worksheet, from last week's worksheet, right? We had this question of like, oh, if we map Z20 to Z20 and we know that phi 5 equals 5, what are the possible isomorphisms? So we looked at maps from Z20 to Z20. Such. And in that case, we had a restriction on the automorphism, and we generally won't have this restriction. But so, if we talk about isomorphisms from Z20 to Z20, we're talking about automorphisms, right? And so we had this guarantee, and in that case, we discovered, what was it? So we discovered that phi of x was equal to x. That was one option. This was another one. And 17x, okay? So these are the things which satisfy phi of 5 is equal to 5, okay? So these are examples of automorphisms. Okay, and the question, a good question might be like, is that all of them, right? Did we manage to get them all? And I'm trying to think, no, we didn't. We missed a few. So there are actually a few more. Does anyone know what they are? Like if you had to guess, like what's so special about an automorphism, could you tell me what, which ones do you think we missed? I'll give you a hint. There's 1, 2, 3, 4, 5, 6, 7, 8. There's 8, so we missed 3 of them. X to negative X. So that would be the same thing as going to 19X, right? Like X mapping to negative X, because negative X is, or negative 1 is the same thing as 19. So yeah, that is 1. Okay. Any other ones? Actually, I'm a little bit concerned here because I feel like 5X shouldn't have been 1. Yeah, 5 actually shouldn't. Oh, you know what it is? Okay, last week's problem said, what are the possibilities? This one actually isn't an automorphism, right? That one actually isn't. Is 9? 9 is, 13 is, 17 is, 1 is. Yeah, let me just give you the other ones. Maybe let me call these phi 1, phi 9, phi 13, because they're different automorphisms, right? What's the other one? Phi 3, phi 7. 9 is 11, 1. 11 is also 1. Okay, we got 13, 17, and 19. Okay, here's all of them. Does anyone see the pattern? What's the pattern? So it's not prime. No, not prime. I anticipated you were going to say that because 9 is in there. Coprime with 20, right? So notice, and 9 was the only one, right? So you're right, that was kind of mean because you look at most of them and you're like, oh yeah, they're all prime, except for that one, right? 9 kind of throws this off a little bit there. So notice that 1, 3, not 5, right? Because it's not coprime. 7, 9, 11, 13, not 15, 17, 19 are precisely the numbers which are coprime to 20. Okay, so that seems like that's probably a cool thing that we could generalize. You, of course, should check that each of these is an isomorphism, but we'll actually prove something a little bit later that will make that very clear, right? We'll basically end up proving it directly. Now, we have dealt with things that are coprime before, like what? Note that this is the same thing as U20, at least as a set. So note that, therefore, the automorphism group of Z20 is in bijection with U20, right? Because U20 is a set of all things which are coprime to 20, right? It's the multiplicative group, but we said that you have an inverse if and only if you're coprime. Both of these, U20 on the right-hand side is a group. I wonder if the automorphism set is a group, right? And then if they are a group, are these two things isomorphic as groups? So that's kind of where we're going to go now. So proposition for any group G, Aut G, so the collection of all automorphisms, is a group under, if you had to guess what the binary operation was, what would you guess? I've got a collection of functions, they map G to G. What would be the binary operator? Any guesses? Exactly, composition, right? And composition makes sense because, and only makes sense because it's an automorphism, right? Because it maps G to G. So if we just kind of think about this before we actually kind of prove it, so if we compose two automorphisms, well, it makes sense. You can actually do that because it'll map G to G, and then when you compose it, it'll map G to G again. So the composite map also maps G to G. Inverses should exist, right? Inverses will exist because they're isomorphisms, right? And precisely, we know that isomorphisms have inverses that are also isomorphisms, right? So inverses will exist. Function composition is associative. Boom, no problem, right? So it seems like everything here should work out. What's the identity? That's maybe the only thing that we have to think about a little bit. What should the identity element be for this group? Any guesses? No? So it would be the identity map, right? The map which just sends little g to little g, which doesn't do anything. So the identity map, right? X maps to X, f of X equals X. That is the identity element under composition, right? Okay, so first note that the identity element is this thing, which just maps little g to little g. Okay, so this is certainly an automorphism. And the special property of the identity is that when you compose it with any other function, it doesn't do anything, right? And for any phi and odd g, phi composed with the identity is the identity composed with phi is just equal to phi. And that's exactly what you want the identity to do, right? So we have an identity. Function composition is well defined. Since if phi and psi are automorphisms, then phi composed psi is an automorphism. I guess we didn't prove that the composition of isomorphisms is an isomorphism, but that proof is very easy. Okay, so a good exercise should be very, very quick. In fact, there's a one-line proof to it if you think about it. But if I give you two isomorphisms, any isomorphisms, but make sure their domains and codomains make sense so that you can actually compose them. If I give you any two isomorphisms, their composition is also an isomorphism. And in fact, you need this so that being isomorphic is an equivalence relation on the set of groups, right? So if G is isomorphic to H and H is isomorphic to K, G is isomorphic to K. How do you do that? Take an isomorphism from G to H, an isomorphism from H to K, you compose them, gives you the isomorphism from G to K, right? Very easy to do. So check this, it's a one-liner. So composition is well defined and there's an identity. What do we need to check? Associativity, boom, it doesn't, we don't need to prove, you never need to prove that function composition is associative. That's always true. Okay, you should say it, but you never have to prove it because it's just always, always true. And then finally, the existence of inverses, but again, they're isomorphisms. So by definition of an isomorphism, it has an inverse and that inverse is also an isomorphism, which would also therefore be an automorphism. So finally, if phi mapping G to G is an isomorphism, then its inverse is also an isomorphism, right? That's what we proved the other day. Remember when I went on my long spiel about saying, oh, like, I don't like how we define isomorphisms in most, like not just this class, but like all group theory classes, because the true definition of an isomorphism should be that its inverse is an isomorphism as well. Well, suddenly you can see we're actually using it here, right? And since its inverse is an isomorphism, well, from G to G as well, it's also an automorphism. So yeah, this thing is a group, right? And again, kind of under our realization above that Z20, the set of all automorphisms of Z20 looked like the multiplicative group of Z20. Maybe we'll be able to prove that those two things are isomorphic in general. Maybe the automorphism group of Zn is precisely Un. Okay. Spoiler, the answer is yes, and we will prove it. But let me, I want to write down a little exercise for you here. This is a really hard exercise. Okay, if you can't get this one, don't worry about it. Okay, so the automorphism group of U12 is isomorphic to S3. Turns out those are the same group. It is not at all obvious. This is a very, very hard exercise to prove. I mean, it doesn't seem like it should be too bad. The thing on the right only has 6 elements in it, right? The symmetric group on 3 letters has exactly 6 things in it. And the left-hand side, U12, only has 4 things in it. So if we're looking at the collection of all possible automorphisms from a set with 4 elements to a set with 4 elements, it doesn't seem like there should be too many. In fact, you can show pretty easily that there's exactly 6 of them. So you can basically just do it by hand, right? You can basically just say, oh, let me write down all the automorphisms on the left-hand side and then figure out appropriately what to map them to in S3. Now, the reason why this is hard is because for your purposes right now, you kind of just have to do this the hard way. Like you have to just brute force it and compute what all the automorphisms is. There is a more clever way, but we're not there yet, okay? Because we haven't, for example, talked about the Klein-4 group or products of groups or anything like that. Once we have that, this proof becomes very, very quick. And you actually need a little bit of linear algebra for the quick proof too. But until then, right, you can just give this a shot. It is actually a fun exercise, if not a little bit tedious. Okay, so give that a shot. Okay, so do I now want to prove that Zn is isomorphic to Un? Let me just see what I put in my notes. Yeah, we're going to do it. Okay. So before I'm going to do that, oh no, let's just state it as a theorem. Okay, so theorem. So for all, I guess we'll just say N in N, the automorphism group of Zn is isomorphic to the group of units mod N. Okay. So a couple of critical things here for this proof are going to be the following. Recall that last Tuesday, I told you that an automorphism of Zn, I didn't use the word automorphism at the time, I said isomorphism, but an automorphism of Zn is entirely determined by what it does to the number 1, right? So recall, in fact, any homomorphism of Zn, not even an isomorphism, any homomorphism is entirely determined by what it does to 5, 1. So recall that homomorphisms are entirely determined by what they do to 1. Right? And what I mean by that so if we take a map and I look at, what phi of 1 is, or let's say phi of n. So let's say k. So it's phi of 1. And I wrote this exact thing last time, so this isn't crazy. I might have used different letters. But I wrote more or less this word for word. Right? So because it's a homomorphism, I can split it up like this. And that is precisely k times phi of 1, right? And this is true for all k and Zn. So this is what I mean by a homomorphism is entirely determined by what it does to the number 1, right? And generally, this is sort of true for cyclic groups, right? If your domain is a cyclic group, then you're entirely determined by what you do to a generator of your domain, right? So the domain is generated by some element little g. You know that its image is also going to be cyclic, and in particular is just going to be, acting a certain number of, what do I want to say? Basically, you can pull the exponent out of phi. In this case, I've kind of written it additively, but you can pull the exponent out of the phi and, again, entirely determine what the homomorphism is just by what it does to a generator. One here generates Zn, so that's kind of exactly what we're saying. So two isomorphisms are the same isomorphism, or two homomorphisms, I should rather say, are exactly the same if and only if they map one to the same thing, right? So convince yourself. It's like a two-line proof. That phi equals psi if and only if phi of 1 equals psi of 1. Okay, it's very straightforward. Like each of those directions is one or two lines at most, right? I mean, the forward direction is immediately obvious, right? If the two homomorphisms are equal, then they must send one to the same thing, right? And then in the backwards direction, suppose that they, phi of 1 is equal to psi of 1. Well, by the work that we just did, literally above, I therefore know that phi of k is equal to psi of k for all k. Boom, I'm done, right? So it's actually the whole proof, both directions, is only one line, because you only have to prove the backwards direction, and we basically already did that, right? Because now phi of k is equal to psi of k for all k, therefore the two functions are equal. Okay, so again, there isn't really anything to prove there, but you want to stare at that for a little bit and just make sure you really convince yourself that that's true, okay? So they're entirely determined by what they do to the number 1. So now my claim, so this is all homomorphisms, okay? Not just isomorphisms. And notice Zn and Zm have different numbers there for domain and codomain. So now we're going to take the special case, because remember what I'm trying to prove. I'm trying to talk about the automorphisms of Zn. So I'm going to take the special case where we're dealing with isomorphisms, and the domain and the codomain are the same Zn, right? So claim phi from Zn to Zn is an isomorphism if and only if Zn is generated by phi 1. Okay, and then we'll be done, right? And then we'll really, really be done. Because again, we know that the generators of Zn are precisely the elements which are co-prime to n, right? So what that means is you'll be an isomorphism if and only if phi of 1 is co-prime to n, right? And now if phi of 1 is co-prime to n, well, that's precisely what it means to be in un, right? That means that phi of 1 has to be in un, and then we'll basically be finished, right? So we need to prove this claim first. Okay, so proof. So let's prove the forward direction. So let's suppose that phi is an isomorphism. Okay, so I want to show that every element in Zn is in the set, or is in the group generated by phi of 1, right? So the critical thing that I'm going to need here is that phi is surjective. So let's say let K be an element of Zn. Since phi is surjective, there exists, I don't know, what do we call it? L in Zn? So that phi of L is equal to K, right? And the reason that I want to do that is precisely so I can use my trick above, right? I can write it in terms of phi of 1. Maybe if I write this the other direction, it'll be better. So that K is phi of L, which we know is L phi of 1, right? And since I've written now as K times L phi of 1, that means K is in the subgroup generated by phi of 1. Thus, what have I shown? I've shown that Zn is a subset of phi of 1, but the other direction is trivial. And so they are in fact equal. Right? So I didn't even need injectivity there. I really only needed surjectivity. But I mean, once you have surjectivity of a map from Zn to Zn, you have injectivity automatically too, right? So I used only surjectivity there for from the isomorphism property. Now, if we prove the other direction, well, it suffices to prove that, you know, so again, I should say, okay, maybe I should say this. I guess I should have included this here. I'm really sorry. So not just any function, right? But a homomorphism. So we're already assuming that phi is a homomorphism. I really should have said that. Okay. Obviously, I can't take any function for which this is true. I'm specifically taking the homomorphism for which this is true. And this is what I'm claiming here. What I'm testing is a condition for which a homomorphism is an isomorphism, right? Because in Z20, phi of x equals 5 times x is a homomorphism, but not an isomorphism, right? And in particular, that's because phi of 1 equals 5 does not generate Z20, right? It only generates the cyclic subgroup of order 4, right? 0, 5, 15, or 0, 5, 10, and 15. Okay, so in the other direction, it suffices to show. So again, I'm already assuming that my map is a homomorphism. So all I need to do is show it's a bijection. And I claim that it suffices to show that phi is surjective. Okay, now I want to make sure everyone's okay with that. I'll give you a second to catch up and then think about what I wrote down. So it suffices to show that phi is surjective. I need to show phi is bijective. And I'm claiming I don't need to prove injectivity. Why don't I need to prove injectivity? Somebody tell me. This is a really useful thing to keep in mind. If you've forgotten it from Math 102, why do I not need to show injectivity to conclude bijectivity? Or conversely, if I only proved injectivity, I wouldn't need to prove surjectivity. I only need to prove one of them. Does anyone know? Anyone remember? Why don't I need to prove the other one? Sure, yeah, yeah, well, okay, yeah. So, I mean, you're both kind of on the right track here. I think we can maybe say it a little bit better. A function, if A and B have the same cardinality, right? Maybe let's kind of put that in the side here as a comment. If the cardinality of A is equal to the cardinality of B, and F mapping A to B is surjective, then it's bijective. I don't know if this was ever proven in 102. It's certainly a 102-ish type of proof. Same sort of thing. You could replace surjectivity here with injectivity, but think about it. You have the same number of elements, and I should say that these are both finite, right? This will not hold if you're not finite. But if the domain and codomain have exactly the same number of elements, and I give you a surjective map, I can't possibly have mapped two things in A to the same thing in B, right? I have to be injective because I only have exactly the right number of elements to hit everything in B. So if I hit everything in B, I can't afford to spend, to be wasteful with my elements in A. Exactly, it's basically a pigeonhole, right? Or it's kind of like an inverted pigeonhole in some sense, right? Like pigeonhole is usually, I'm forced to send two things to the same thing. So it's kind of like an inverted pigeonhole where I have n pigeons and I have n holes, and I guarantee that every single hole has a pigeon in it. Well, there's no way I put two pigeons in the same hole, right? N holes, n pigeons. Every hole has a pigeon. I can't have put two pigeons in a single hole, right? And it's the same thing with injectivity. So if I know that I'm injective, so namely I have n pigeons and no two pigeons can go into the same hole, then I get surjectivity for free. I had to have put a pigeon in every hole, right? So the cardinality condition here actually means if the domain of A and B are the same and they're both finite here is important because you don't have an infinite pigeonhole principle. If A and B are finite and you have an injective map, then you actually have bijective. And I think you've seen something like this in linear algebra too, right? In linear algebra, you have a similar sort of thing. If you have two vector spaces of the same dimension, right, and dimension is finite, then an injective map is automatically a bijection, and our surjective maps is automatically a bijective map, right? Because you have to map basis elements to basis elements. And so an injection of the one set of bases to another set of bases is automatically a surjection as well, right? Do you remember that sort of thing? Yeah, exactly. So what I'm saying here is you only have to prove one of them. This is really useful. Injectivity is not impossible. It's not, but it's way harder than surjectivity, right? So this is a really useful thing. Keep it in mind, especially since almost all the groups that we deal with in this course are finite, right? So if you're trying to show bijection, you only have to show one of them. As long as you know that the domain and codomain have the same cardinality ahead of time, which in this case they do trivially, right? They're literally the same set, right? Look at the definition of phi at the top of the screen. There's the same set, right? Okay, so we want to show it's surjective. So let's say let M be some element of Zn, but we know that Zn is generated by phi of 1. So M is equal to k phi of 1 equals phi of k for some k. Thus, phi is surjective. Right, and I'm done. Or at least I'm done the claim. Okay. All right, let me zoom out here and let's see what we've done. Because this proof, we probably forgot what it is we were actually trying to prove. So I said, at this point, we're basically done, but you still would be very reasonable to say, well, I haven't actually proven this yet, right? I've shown that there is this sort of bijective correspondence between isomorphisms or automorphisms of Zn and Un, but I still have to show that they're actually isomorphic as groups, not that there's just a bijection between them, right? That's what I've done up until this point. I've shown that there's a bijection between them, that every, right, what's the claim say? You're an isomorphism if and only if phi of 1 generates the group, i.e. if and only if phi of 1 is co-prime to n. And phi of 1 entirely determines the isomorphism, right? So at this point, I've shown there's a bijection between UN and the automorphism group Zn. And now I need to show that there's actually a group isomorphism between them, right? Bijection is not sufficient. Okay, so finally, so we're going to define, I'm going to use capital phi here. It looks kind of like the green lantern symbol. That's a capital phi. Okay, and I'm going to define it in the obvious way by taking phi, which is the automorphism, to phi of 1, right? So I'm saying you give me an automorphism, and the output of this map is to tell you what phi of 1 is, right? And we know this is well defined because we've already said that you're an automorphism if and only if phi of 1 is coprime to n. So this is well defined by our conversation above. Right? Where we said you're an automorphism if and only if phi of 1 generates the group, if and only if phi of 1 is coprime to n. All right. And again, we already know that this is injective. Is injective from, I guess I didn't label it. Let me call it star. Okay, and I'm going to move my screen up here because the comment star is not on the screen anymore. So if you're taking notes, I need you to look at the screen right now because I'm going to go up, label the equation, and then come back down. Okay, so pay attention to the screen right now. So I'm claiming that phi is injective from star. Star is this statement right here. Okay, that two homomorphisms are the same if and only if phi of 1 is equal to psi of 1. That is precisely the statement that this map is injective, right? Since if phi of phi is equal to phi of psi, that's true if and only if, well, the outputs of these things are phi of 1 equals psi of 1, and that's if and only if phi equals psi, right? So that gave me injectivity. It's surjective, and here I actually do need to prove both because I don't know what the size of the automorphism group of Zn is. I've claimed that it's bijective. I mean, we really should, I think in this case, prove it. But again, that's obvious. It's surjective since if, let's say, K is in UN, then phi of X equals KX is an automorphism. By double star. Okay, again, I'm going to scroll up here. Okay, so by double star is the statement. So if Kn is, then phi kx is an automorphism by blah, is a statement by our claim, right? This is the claim, right? So you're an automorphism if and only if phi of 1 generates the group, if and only if, phi of 1 is coprime. Here, K is exactly equal to phi of 1, right? Since phi of 1 equals K is coprime to N. Okay, and so the last thing is just to prove that it's actually, so we know it's a bijection, so we just need to show it's a homomorphism. And finally, okay, this might be the only one you have to stare at for a second and be like, wait a second, is that true? Okay. So this line right here, so I claim that, yes, this is true, and it's obviously true, but you're going to have to stare at it and think about it for a second. In green, I've written that phi of k is equal to k times phi of 1. So let k be psi of 1, right? So if k is psi of 1, then phi of psi of 1 is phi times 1, or phi of 1 times psi of 1, right? That's what this equal sign is. It's the only one that you kind of have to think about, but we know that it's true from, again, the very first thing that we did in the proof. And thus we've shown that phi is a homomorphism. I should just say it's an isomorphism. And we're done. Right? All right. I'm going to zoom out, see if I can get the whole proof in here without it being too small. Whew. That's a little bit of work, but at the end of the day, none of the claim is that like we had the intuition, right? The intuition behind why it should have worked. And yeah, okay, we kind of had to go through the motions of putting everything together in order to make sure that, you know, we could construct the proof. But at no part was the proof, I think, like overwhelmingly difficult. We just had to kind of think about, this is the big thing that I'm trying to show. How do I break that down into smaller pieces and then show each and every single one of those pieces? And now that we're doing a third-year course, you know, suddenly we can be expected that our proofs are starting to get a little bit longer, right? Gone are the days of the relatively simple proofs. Sometimes now we have to put things together and make them a little bit bigger. But again, hopefully we had that idea from the very beginning about why this was true. And I hope that you believe that I think many of you could have constructed this yourselves, right? That I didn't do anything here that was too crazy. I just kind of broke it down into a couple of pieces that were easier to digest and to prove. Okay, so are there any questions about that? And I mean, anytime, unfortunately, you know, you're doing a proof with like isomorphisms, there's stuff you got to prove, right? You got to prove that it's homomorphism, you got to prove it's bijective, you got to prove it's injective. And so your proofs get a little bit longer just by virtue of the fact that there's a couple things you got to prove, right? Okay, yeah, okay, that's right. Let me see if I can maybe break this down a little bit better. Okay, so remember, we're trying to prove that the automorphism group of Zn is equal to Un. So maybe let me put some cliff notes on the side here, okay? So here, I'm making the statement basically that homomorphisms are entirely determined by what they do to one, right? Right? That's what that chunk of is saying. In the same sense that when you have a linear isomorphism between vector spaces, an isomorphism of vector spaces is entirely determined by what you do to a basis, right? Because you know that you can write every other element of the vector space in terms of that basis. So if you know what the basis elements map to, you're done. And if you think about it here in the same sort of way, one is like a basis element because you can write every number in Zn as, you know, some linear combination of ones. And so if you determine what one maps to, you're done, right? So that thing, what we're saying is the all homomorphisms are just defined by what they do to one. Okay, now here, what we're trying to do is characterize what sorts of homomorphisms are isomorphisms. So which phis are isomorphisms. Okay, but instead of looking at phi, by the previous thing, we've learned that it actually suffices to just look at what phi of ones would work. So we do this by looking at phi of one, because we said phi is the same thing as phi of one. If you know what phi of one is, you know what phi is. And if you know what phi is, you know what phi of one is. So those are the same thing, right? We're basically saying, I'm going to think of every homomorphism just in terms of what it does to the number one. I don't care about what it does to anything else. We're just going to make that sort of identification in our brains. What is the homomorphism and how does it, well, the identification in our brains is identifying a homomorphism with what it does to the number one. So which of these homomorphisms are isomorphisms? Oh, it's the ones where phi of one generates all of Zn, right? And therefore is the ones for which phi of one is coprime. So we do this by looking at phi of one and showing phi1 is coprime to n, right? So that part is us showing that whatever phi of 1 is, if it's an isomorphism, it must be because phi of 1 is coprime to n. And then here is where we finally show that there is actually an isomorphism. So actually constructing the isomorphism. Does that help? Kind of like that kind of bigger picture of how this has been broken down, right? Characterize the homomorphisms by what they do to phi of 1. If I want it to be an isomorphism, phi of 1 has to be coprime. And now let's actually do the isomorphism, right? Yeah, okay, perfect. Hopefully that helps out. And again, sometimes this can be a little bit tricky because we're talking about like capital Phi is a function of functions, right? And there's a little bit of like brain accounting that we have to do here because again, you know, automorphisms, the automorphism group of Zn is a group of functions. There's a lot of stuff going on there, right? We've got functions which are already kind of tricky and they're functions of groups, which is itself a group. And now I've got a function mapping that thing to another group, right? Capital Phi is a function mapping a group of functions of a group to another group, right? What a tongue twister that is when you kind of unravel all the definitions. So there's a lot of sort of like intellectual accounting that has to go on and it can be easy to be lost in the details, right? But just, you know, take it slow and try and think about what's going on. Yeah, I think that like, you know, and me too, when I was an undergrad, when you start dealing with functions of functions, it takes a little bit of time to get comfortable with it. But unfortunately, you have to, because if you're going to do, especially any sort of higher math, functions of functions are things that we do all the time. But in fact, you did this a little bit when you were in calculus, right? You would have the derivative operator, which, you know, ate a function and then output a function. So you could think of it as a function of functions, right? The derivative operator was a map from the differentiable functions to the continuous functions. And same thing, the integration, right? Antiderivatives, an integral ate a continuous function and outputted a continuous function. So, you know, we've seen functions of functions before, but it definitely takes a little bit of time to sort through all that. Okay. All right. Why don't we take, I guess we're at the hour mark here. Why don't we take a 10-minute break or so? Maybe let me leave this whole proof up just so if you want to stare at it a little bit more, you can. But let's take a 10-minute break. I've got 2:01 by my watch here. So we'll come back at 2:11. Okay. How's that sound? And then I'll talk to you about what an inner automorphism is. So not only an automorphism, but now it's a very special type of automorphism. All right, so let's try that. And let me stop the recording now, or pause it. Okay. So let's get back to it. Now, like I said, we're going to talk about a very special kind of automorphism, something called an inner automorphism. And there will be things called outer automorphisms, but the outer automorphisms are defined in terms of the inner automorphisms. And let me tell you, this is my jam. This is inner automorphisms are one of my favorite things, just because they show up a lot when you do like Lie groups and Lie theory. And I've told you, like, you know, in terms of me as a group theorist, the group theory that I did was not discrete group theory, right? Like I don't work with finite groups. I deal with topological groups that have, you know, that you can do calculus on basically. And then, so yeah, you take all this and then you throw in calculus as well. And you ask like, what does it mean for these maps to be continuous and differentiable and tangent spaces and all these sorts of things, which, you know, might sound scarier, but is actually like way more fun in my opinion. So that's sort of like a Lie theory thing. If you're kind of interested, Lie there spelled L-I-E, like lie. But yeah, inner automorphisms there are used all the time. They're so crazy important. Because in particular, when you differentiate these, something very important happens. Okay. But of course, we're not going to do that in this course unless I'm feeling mean and I put it on a quiz or something. We'll see. We'll see. Okay, so basically, here's the idea. If G is a group, oh, big G. Why am I using little g? Then we define the conjugation map. And I think for our purposes, we're just going to call it phi sub little g from G to G like this. And the way it's going to work is that if you give me an input, I'm going to conjugate by G. What does conjugate mean? Well, it means this. Okay, so you're going to do GX G inverse. All right. Now, the collection of all of these things is called the group of, or the collection of inner automorphisms. Now, we don't even know that they're isomorphisms. We should probably actually check that, and we will. But let me add this. The set, which we call in, that's pretty universal. This is the collection of all phi g's, such that G is in G, is the group of inner automorphisms. Now, like I said, we haven't proved that each of these is even an automorphism, and we certainly haven't proved that in G is actually a group itself, and we are going to do those things. But just kind of like as a snapshot looking towards the future, yeah, it will be. Okay, so they're all going to be automorphisms, and this is going to be a group and therefore a subgroup of odd G. Okay, so let's start proving those things. And again, the proofs are wonderful in the sense that they're very nice and very easy. And I find like working with automorphisms in general is tough, but working with the inner automorphisms is much more concrete. You can really get a grasp on them and start to, think about what it is that these do. So when you're trying to get an intuition for how to work with automorphisms and, constructing isomorphisms between the inner automorphism group, yada, 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 this is a great place to work, okay? There's a lot of potential for intuition development by playing with the inner automorphisms, okay? So if you're trying to do that, this is a great place to work with. And I really can't wait until next week when we start talking about quotient groups, because there's lots of cool things that you can do with the inner automorphisms and quotients, but we'll get to that. Okay, so proposition, phi G is an automorphism. For any G. Right? Okay, so proof. So I hope I don't need to explain that it's well defined, that clearly GX G inverse is an element of G, right? Because it's just everything is closed under the binary operation. So what do we need to check? We need to check it's a homomorphism, and then we need to check that it is a bijection. Now, again, in terms of bijection, we only need to prove one of injective or surjective, because we'll get the other one for free, because being an automorphism, injection, or being a map from G to G, we only need to prove one of them, right? So let's start with homomorphism. So note that phi G is a homomorphism. And this is the usual trick here. You're going to see this. Since phi G xy, well, if we just define that, what do we get? We get gxy G inverse. And if you think about what I want this to look like, I want this to look like phi gx times phi gy. So I need a G inverse to show up in between. So I'm just going to artificially add these. Gx G inverse, like so, right? Where we do our usual trick of multiplying by 1 by writing it as G inverse G. And this is exactly what I wanted, right? Phi G x, phi G y, voila. So it is, in fact, a homomorphism. And now we just need to check that it is either injective or surjective. I think injective here is really, really easy, namely show that the kernel of phi G is trivial. So it suffices to show injectivity So we want to show that its kernel is trivial. So suppose that X is in the kernel of phi G, right? And I want to show that X is the identity. X should be Y in the line. Oh yeah, you're right. Thank you. Thank you. This should be a Y. Thank you. I got a little overzealous and wrote X twice. Okay, so I'm going to choose an element in the kernel and show that that element has to have been the identity element. So, okay, what do we know then? So the identity is equal to phi G of X. And if I just write that out, I get G X G inverse. And yeah, we're actually done, because now what I'm going to do is I'm going to put the G and the G inverse on the other side, right? So I'm going to multiply on the left by G and on the right by G inverse. So I'm going to get G inverse G is equal to X. And of course, that's equal to the identity, right? So that shows that the kernel phi G is the identity and phi G is injective. And we're done, right? So since it's injective, it's bijective, and it's a homomorphism. Therefore, it's a bijective homomorphism, and so we're done. Of course, equivalently, it would have been enough to just show that there is an inverse map. Can anyone guess what the inverse should be? It turns out it's not too bad. Or maybe let me say alternatively. And we're going to need this in a second, because I am going to show that the inner automorphism group is a group. So we're going to need that inverses exist. But if you had to, like, let's say I gave you phi sub G, what do you think the inverse of that map is? No guesses? Here's a cool thing. Look at what happens here. So let me kind of do this for both of these. So G and H are elements of G, then note that the following is true. Phi of G compose, or let's maybe do phi of G inverse compose phi of G acting on X. So what is that? So that's going to be phi of G inverse acting on phi of G X, right? And now let's just expand this out. So I'm going to get phi G inverse, GX G inverse. Now I'm going to conjugate by G inverse. And so keep in mind, the order here is important. G inverse is going to go on the left, G inverse inverse on the right. But of course, G inverse inverse is just G. So everything here cancels out to give us X, right? And since this is true for all G and for all X, this tells us that phi G inverse compose phi G is the identity map. I.e. the inverse of phi G is phi G inverse. That's cool. And actually, I guess we probably could have done it a little bit faster if I'd done this one first. Well, whatever, hindsight's 2020. So again, if we expand all this out, right? So it also says that phi of G compose phi of H is phi of GH. So here's an interesting thing, right? Like when I compose, which we know should be the group operation on automorphisms, that's the same thing as just multiplying the elements of the group. When I invert the function, which is the notion of inversion in the automorphism, that's the same as just taking conjugation with the inverse element. And I guess finally we should say that if E is the identity, in G, that conjugation by the identity element is just the identity function, right? So what have we shown? So proposition in G is a subgroup of odd G, right? And the proof to that is actually what we just kind of went through, right? I could have stated the proposition first, but this is the sort of thing where you just kind of like playing around. You're like, oh, hey, look, that works out really, really nicely. Right, so it has the identity element. It's closed under function composition, right? Because the composition of two of these things is another one of these things. And it's closed under inverses because the inverse of one of these maps is also a conjugation map, right? Does everyone see that? Are there any questions about that? Right, I've shown that if I compose two inner automorphisms, I get an inner automorphism. And if I take the inverse of an automorphism, of an inner automorphism, I get an inner automorphism, right? And so that's exactly what I need to show that it's a subgroup. That's okay? Any questions there? So one of the great things that you can immediately do is if you choose a small enough group, you can actually just write one of these things down, right? So take an element of S3, for example. So if you choose an element of S3, choose a non-trivial element, obviously, otherwise it's kind of a silly question, but choose, the transposition 1, 2. And just look at what is this inner automorphism, right? Just do 1, 2, X, 1, 2 inverse. And then there's only 6 elements in there's only 6 elements of the group. So you can just compute this for all 6 elements and just see what exactly this inner automorphism does, right? So that's, I think, very nice. It gives you these like really nice concrete examples of automorphisms, especially for non-abelian groups, because that big theorem that we proved above when we were talking about Zn is a very special class of groups, right? Zn are cyclic and abelian. They're basically the nicest groups we could possibly have. So if we want to start getting concrete examples of automorphisms of S3, well, we got to think a little bit more, right? So the inner automorphisms are a natural candidate for that. In fact, one of the reasons why intermorphisms is such a concrete example, you could be like, well, why don't we compute the inner automorphisms of Zn? But what do you think the inner automorphisms of Zn are? Does anyone have a guess? What are the inner automorphisms of Zn? Anyone have a clue for that? Look at the definition. Okay, GXG inverse. Well, Zn has a really special property, right? What makes this property? No one has a guess for the inner automorphisms of Zn? Yeah, it's just the identity element, right? In fact, you can see that if your group is abelian, the inner automorphisms are trivial. Exactly, Justin, yeah. So if your group is abelian, you can put the G and the G inverse together, and the only thing you get is the identity map, right? So if G is abelian, then all of the inner automorphisms are trivial. The opposite direction is also true. All right, so proposition in G is trivial if and only if G is abelian, right? So the proof, let's start with the easy direction first. So let's assume G is abelian. Then for all G's, little g's in big G, we have phi big G of X is GX G inverse, but the group is abelian, so we can kind of regroup this as G inverse X, and that's just X, and that's the identity, right? So every single inner automorphism is just the identity map. So voila, that's all of them, right? I guess up here, instead of writing E, we know what E means, right? But I guess I've said the identity there is the identity map, so. So thus everything is the identity. And the other direction you can imagine is not so much worse. So let G and H be elements of big G, right? And we want to show GH is equal to HG. Like that. And the natural way to do this is to just take the conjugation map and act it on H. So now H is the identity map on H. And well, we said every conjugation map is the identity map, right? So let's just let phi G be the identity. That's equal to GHG inverse. And if you kind of ignore all this stuff in the middle, what do we have? So I'm going to multiply both sides on the right by G. So we get HG is equal to GH as required. That's kind of a slick little thing, I think. Right? Not terribly difficult. But just the assumption that every single inner automorphism gives you the identity map is enough to prove that every two elements have to commute. And maybe that's not surprising, but kind of the proof is slick there. I think that this line in particular here is a little bit slick, right? Because you're saying, I know that every single one of these maps is the identity, but voila, you end up getting that the group is abelian, okay? Now, I guess I don't really want to do my next thing because I actually think it would be a really good test question. So I think I'm actually not going to do it. But maybe let's just do one last thing. So here's an exercise, and I want to see how quickly we can get it. Okay, what is Aut-Z? So Z obviously here I'm assuming is the additive abelian integer, so our usual copy of Z. What is its automorphism group? I claim this question is not difficult. What is its automorphism group? So I'm not asking the inner automorphisms here because we know that's trivial, right? Z is abelian. So by the theorem we just proved, its inner automorphisms are trivial. I claim, though, that the automorphism group of Z is not trivial. Okay, there are other things in there, but there aren't many. So can anyone think of what they could be? Anyone? Okay. Let me ask you the following. Is Zed cyclic? Yes or no? Even if you don't know, guess, it's 50-50. Okay, so I've got a no. Does everyone agree with the no, or? Okay, so we've got two no's. It does have infinite order, absolutely it does. Okay, so we seem to have unanimous no. Actually, Zed is cyclic. Hopefully I just didn't explode too many brains. Zed is absolutely cyclic. It's absolutely generated by what? Every integer is some product of ones or negative ones, right? Remember, when you take the group generated by a set A, you're allowed to use its inverses. No, I'm not using the weird, adding a bunch of positive things as a negative thing. You're allowed to take the inverses as well, right? That's the definition, right? The definition of A is the collection of all words that are either A's or A inverses, right? We said that M had to be some natural number, but then N sub K could be any Z. So you're allowed to use inverses as well when you take the subset generated by A, which means I'm allowed to take negatives as well. Now, our problem here is that when you're all thinking about cyclic groups and you're thinking about finite cyclic groups, you never have to worry about the negatives because you know that eventually, because it's finite, it kind of circles back on itself, right? But strictly speaking, if you take a subgroup generated by a set, you're allowed to use the inverses of those elements as well, right? So is everyone okay here that this is in fact cyclic? If we, again, kind of recall this fact that we're actually allowed to use the inverses of one as well. So certainly every positive number is some collection of adding ones, and every negative number is also some collection of adding negative ones, right? Or alternatively, think about it like this. You know that the subgroup generated by one has to be a group, right? It's always a subgroup. We said that. So what group is it? Well, it certainly contains every positive number. And since it contains every positive number and is a group, is a subgroup of Z, it also has to contain every negative number, right? So if you want to think about it like that instead, you could. But yeah, Z is generated by one. Are there any other generators of Z? So this is what I want to get to. Are there any other generators of Z? Anyone? Negative one. Yeah, absolutely. Okay. So now here's the thing. An isomorphism or an automorphism of a cyclic group must map generators to generators. So automorphisms must preserve generators. Okay, if you don't believe that, prove it. It's basically, we've already talked about it. We already talked about how the image of a cyclic group is a cyclic group, right? Even if you're just a homomorphism, let alone an isomorphism. But we know that the image of a cyclic group must be a cyclic group, right? And if you're an isomorphism, well, then your image actually has to be everything, right? Your range is everything, your surjective map. So whatever your image is cyclic and is everything. So you must map a generator to a generator, right? So go through that, spend some time convincing yourselves that an automorphism must preserve generators. In which case, we only have two generators, right? No other number generates that. Do you agree? Because the subset generated by 2 misses all of the odd numbers. The subset generated by 3 are just all the multiples of 3. The subset generated by 4 are the multiples of 4, right? So as a general rule, the subset generated by n are all the multiples of n. And whether you take that to be plus or minus, you're not going to get everything unless n is plus or minus 1, right? So these are the only two generators. So what this tells you is that there's only possibly two automorphisms. The identity is obviously one, but what's the other one? The other so whatever this phi x is, it has to take 1 to negative 1. What? Yeah, negative x. And these are the only two things which do that, right? Again, the automorphism has to map generators to generators. Phi here maps 1 to negative 1. It also maps negative 1 to 1. And is it possible to map, and the only way to map, okay, let me put it this way. So our maps either have to map 1 to 1, negative 1 to negative 1, 1 to negative 1, or negative 1 to 1, right? These two are the identity, and these two are phi. Do you agree? Because it has to map generators to generators, these are the only two possibilities. There are no other generators. There's only 4 ways of mapping generators, and actually each of these automorphisms take care of 2 of these cases. So this is all of them. And there's only one group of order 2. So the automorphism group of Z is Z2. Okay, now you might want to go through this and do this one a little bit more rigorously. This is just kind of like the rough idea that I'm trying to give you here. You should show that automorphisms preserve generators, but once you have that, then you're done. Because if you want to prove that the automorphism group of Z is equal to Z2, you just say, well, like, listen, suppose it's not. Suppose there's something else. Well, then it has to map a generator to a generator. And again, it still has to be defined by what it does to the number 1. Z is cyclic and abelian. It's entirely determined by what it does to 1. So just like we did for the other finite groups, right? This case is still true. So if you want to do it a little bit more rigorously, you can, but this is the rough idea. Okay, it's not even the rough idea. Like this is 90% of it. But I guess there's actually kind of an important thing to say here as well, which is that like as the group gets bigger, you don't necessarily get more automorphisms, right? Like this is the, like other than being the trivial group, this is the smallest the automorphism group could be, right? And not be trivial. But Z is much bigger than Zn, right? Z has infinitely many things. Zn only has finitely many things. So even as the group gets bigger, that actually doesn't guarantee that you get more automorphisms. You could actually get less automorphisms, right? And I mean, hell, actually, we kind of knew that from, where the hell is it? From this theorem, right? That the automorphisms of Zn are isomorphic to Un, i.e., right? Actually, if we kind of want to add a little comment here, right? The order of the automorphism group is the same as the Euler-Toshin function. And we know that thing just is all over the place, right? If n is prime, then phi n is n minus 1. But even just the next number bigger, it could be significantly smaller, right? Like when n is 23, the size of the automorphism group is going to be 22. But when n is equal to 24, it significantly shrinks, right? So it's very, very hard as a general rule to figure out how big the automorphism group is going to be. Actually, I guess I gave another example up here too, right? This exercise showed that the automorphism group of U12 is isomorphic to S3. U12's got 6 things in it. Its automorphism, or U12's got 4 things in it, but its automorphism group is non-abelian and isomorphic to S3. We can't even tell abelian and non-abelian, right? Zn is abelian, S3 is not abelian. Now, there's no reason to suspect in general that automorphism group should be abelian, because you know that function composition is not generally commutative, right? But nonetheless, we've got lots of examples where the automorphism group is commutative and a couple examples where it's not. All right. So it's very difficult to just look at a group and determine what its automorphism group is. You generally have to really dive into it and just start playing with stuff. And unfortunately, there's no really any two ways around that. You just got to do a lot of playing around. Okay. Are there any questions? Otherwise, I think I'm actually done. Like, I don't have anything more. This section also does, like, part of the readings for this week include Kaylie's theorem. Now, I haven't seen too many actual practical application of Kaylie's theorem outside of a couple of kind of niche-y things. But all you just really need to remember from it is that like every group embeds as a subgroup of the permutations on it, right? Again, in some obvious way, like what are functions on it what are functions on a group? They're basically a permutation of the group, right? And yeah, that's basically just what groups do, right? Is they permute things. So I don't think Kaylie's theorem it's one of those theorems where I look at it and I'm like, oh yeah, I probably could have proven this. And so it's too bad I wasn't born 300 years ago or whatever the case was. Get all that low-hanging fruit, along with de Moivre's theorem. That one makes me so upset that he actually got his name on that one because it's so easy to prove. But yeah, whatever. Okay, I'm done. I'll obviously hang around for the next 15 minutes and then the hour after that because it's my office hours. But if anyone has any questions, please don't hesitate to ask. Otherwise, you are free to run away now and think and daydream maybe about your automorphisms. Like I said, it's very hard though. Don't just choose a group and try and guess what its automorphism group is. These are generally pretty tricky things to do. But I would love it if somebody managed to solve this exercise. I'd be so happy. Okay. Anyway, everyone, no problem. See ya. For those of you who aren't going to hang around, see you later. I'm going to stop the recording. There's no point to keep recording.